Okay. Hello. Hi. So welcome to today's seminar. Our first presenter will be Marwan Mbarak. He's studying computer science at ETH in his third semester of bachelor's. And he grew up in Luxembourg and has roots in Tunisia and Germany. So he's going to present an interesting work which uses reinforcement learning for data placement in hybrid storage systems. Marwan, please go ahead.
So hello everybody. Today I will be presenting Cibil adaptive and so the paper called Cibil adaptive and extensible data placement in hybrid storage systems using online reinforcement learning. It was presented in the conference ISCA 22. So let's begin right away. First, First for the executive summary. We will be talking about hybrid storage system throughout the paper, how hybrid storage systems use multiple different storage devices of different size and latency, so as to foster the best performance at the best possible cost, and also have the highest storage capacity possible. So the problem, first of all, the challenge that arises with hybrid storage system is a correct or a good data placement policy, such that you can actually foster this performance. For instance, if you were to put everything into the slow device, then there's no point in having a hybrid storage system. The shortcomings of prior data placement policies were a lack of adaptivity to workload changes, and also a lack of adaptivity to changes in device types and configuration. And also there's a lack of extensibility to more devices. So what we want to try and do, what the paper tries to do, is to solve this adaptivity issue and this extensibility issue by providing continuous learning and also adapting to the applications and underlying device characteristics. So this is being solved by what is called Cibil. It's the first reinforcement learning-based data placement technique in hybrid storage systems. And it basically solves these issues more or less by being adaptable to different workloads and also being extensible. We will see later what this means. To a higher number of storage devices. And also on top of everything, it provides an ease of implementation for the engineer that wants to implement data placement policy. The results of Cibil are pretty good. It has a performance improvement of 21.6% over the best previous data placement policy technique. And in 3 hybrid, so in HSS configurations with 3 devices, it improves compared to the state-of-the-art policy by 48.2%. And also it has 80% of the performance of an Oracle policy that knows all future access patterns with a pretty low memory or storage overhead. Now, let's move on to the first point of our outline, which is the shortcomings of prior data placement techniques. So those that already exist in the market and that are out there. So first, let's have a background of what actually a hybrid storage system is. So in a hybrid storage system, as I mentioned earlier, you have a fast device and a slow device. Or if you have a tree hybrid system, it's called, you might have a fast device, then a middle device, and then a low-end device. And these basically can, so you can move data from the slow device to the fast device, which would be a promotion. you can move data from the fast device to the slow device, which would be an eviction. And all of this is managed by the storage management layer, which processes read and write requests from the logical or from the operating system, so from the processes running in the operating system. And then for a write request, it decides to which device it's going to write, and for a read request, it decides whether to keep the page inside of the, so whether to do a promotion or an eviction. And so, yes, moving on. So first of all, the challenge, as mentioned earlier, is that you need a good data placement policy, which will be inside of the storage management layer to foster the best performance, because if your data placement policy is bad, the hybrid storage system is useless. And this is the whole challenge also that this paper is posing itself. Now, to the point of this outline, we observe two major shortcomings of previous data placement techniques, which are first, a lack of adaptivity to workload changes and to changes in device types and configuration. We will see later in more detail what that is. And there's also a lack of extensibility to more devices, which means when, for instance, you go from a hybrid storage system with 2 devices to 3 devices, it's very hard to adapt to keep to use the same data placement policy for the 2 configurations. Now, as for the lack of adaptivity to workload changes, we can observe this using a graph. Here you can see on the x-axis are different workloads that certain data placement policies have been trained on. And you can see on the y-axis is what's called the normalized average request latency. It's normalized to a fast-only data placement policy, which would be basically as if the whole hybrid storage system was only the fast device. And so we have two different data placement techniques. The first one is based on heuristics, and the other one is based on supervised learning. And we compare this to the Oracle data placement policy, which is a fictional data placement policy, which would know all of the all of the access patterns and always takes exactly the right decision. And you can see on some workloads, they're doing rather well. You can see these 2 workloads, it's pretty close to the Oracle policy, which is the best possible latency it could have. Whereas on other workloads, the 2 data placement strategies are just very, very bad, or at least differing much more from the Oracle policy than in the first 2 workloads, which leads to an unsatisfactory average. And so while data placement policies might be doing good, so while the prior data placement policies might be doing good on some workloads, there are workloads which might be unseen or very different from what they have been trained for, or from what the heuristics are based on, to which they just will not adapt. So there's also a lack of adaptivity in device types and configurations. So for changes in device types and configurations. So this happens especially, what is meant here is if you use the same data placement policy for 2 different configurations that have a huge latency gap, or where there's a change in latency gap between the 2 devices, you will have one HSS configuration where it might perform pretty badly. So here we have added the slow only policy, which would be using only the slow device, which is a bad policy, and you always want to be below this one. So here you can see the latency is increased compared to the slow only in the first configuration. Whereas if you have the same data placement policy and the same workloads for configuration with a different latency gap, it will be doing much better. And so this is also not very desirable, because you would want data placement policies to be able to adapt to changes in device types, for instance. And you don't want to make a new data placement policy every single time your device changes or whatever. So there's also a lack of extensibility, which comes from the fact that rigid techniques that require significant effort to accommodate more than 2 devices are being used. And so basically what this really means is, when you have a change in storage configuration, which would be going from, for instance, a dual HSS, so with 2 devices, to a tri HSS with 3 devices, you're going to have to make a completely new design data placement policy. And that is a very huge effort for the engineer. And it's very cumbersome to just every time have to make a new policy when you want to add or perhaps remove a device. So the goal here, as mentioned, is you want to have adaptivity by continuously learning and adapting to the application and also to the device characteristics. And you also want to have easy extensibility. So you don't want to have such a huge engineering effort when you're just adding or removing a device. And that way you can also just incorporate with one data placement strategy a huge range of hybrid storage configurations. So the paper introduces Cibil. Now, to explain the picture, in Greek history, Cibils used to be oracles. So it's really to show that Cibil is performing very well compared to the oracle policy. So Cibil formulates data placement in hybrid storage systems as a reinforcement learning problem. And we will see now what that really means. How do you formulate data placement using reinforcement learning? For that, first you need to know what exactly is reinforcement learning. So it is a type of machine learning model in which you have an agent and an environment. The agent receives a state continuously from the environment, and then it uses that state in order to decide. So it has an inference process inside of it, and then it decides what action it's going to take among a range of actions, of possible actions that it could take. And then the action is performed on the environment, and based on certain metrics, a reward is calculated, and the agent is trying to maximize that reward. So what does that look like for data placement? You have the agent is Cibil. The state is a certain number of features of the current request and the system. We will see what features how that would exactly look like. The action is basically for every single request, you select in which storage device the page will be after the request. So if it's a write request, it's basically, do you write to one storage device or the other? And if it's a read request, it's, do you do a promotion or an eviction? But really the action will just be the storage device, and then automatically promotion and eviction or whatever will be done. And the reward is calculated based on a request latency. So we're trying to minimize the request latency. So first of all, what is the state? In the state we have, or what does the state look like? In the state, there are a limited number of state features. Unlike other machine learning models in which you might have a very, very lot of state features that the neural networks are trained on. So this first reduces implementation overhead. And also, we will discuss that also later. an RL agent happens to be more sensitive to reward, and it doesn't actually need such a huge state vector in order to still maximize its reward as best possible. There is a so the state itself looks like a 6-dimensional vector of state features. So in there you have the size of the page request, you have the type of the request, is it a read or write request? You have the interval, access interval, that is when was it accessed the last time, how many times has it been accessed, etc., etc. But it's really just 6, so a quite limited number of state features. And also to reduce storage overhead again, we're quantizing the state representation. So how do you say, the values are going to be levels of magnitudes and not actual floating point values. Yes. And so what is the reward? What does it look like? Now the reward defines the objective of Cibil, as already, so yeah. And the reward in this case is calculated based on the request latency, so such that it minimizes best possible, or by maximizing the reward, you minimize the request latency. And having such a reward, it encapsulates 3 key aspects, which is first, you can see already from the reward the internal state of the device. Since we're using the latency, if the latency increases, for instance, or from the latency, you can read the information of Cibil itself can read what are the read-write latencies of the different storage devices. It can read the latency of garbage collection, queuing delays, etc. You don't need to put that in the state. By minimizing the request latency, you maximize the throughput, and you also minimize evictions. So yes, evictions would be going from the fast storage device to the slow storage device. So yeah, there are more details in the paper, also a discussion. We will see later more points in the discussion about the reward. Now, what is the action? To skim quickly through it. So as I have mentioned, the action is basically you just selecting a storage device in which the page will end up in. So yeah, also the good thing about Cibil is that you can just extend the action to any number of storage devices by just adding the storage devices to the range of actions Cibil can take. And yes, and Cibil learns, it turns out that Cibil proactively learns to evict or promote pages. And so, yeah. As for a more detailed overview of how Cibil looks under the hood. So first about the Cibil execution. So here we have the Cibil agent. Inside of it, you have the RL decision thread, which is going to take in a request from the operating system. So this is something like, so yeah, it's going to take the request from the operating system and it's going to output a data placement decision. That would be then the action. In the RL decision thread, you have the inference process, right? And concurrently, concurrently you have the RL training thread, which will feed, which will take a combination of the state, the reward, and the action information bundled together, and it will then train and do a periodic policy weight update, which will happen about every 1,000 page requests. And this is an asynchronous execution. We will see later how it is asynchronous. So to go more into detail, we can see here again, there's the RL decision thread and above the RL training thread. And you can also see the storage request going into the RL decision thread. So we will first dive into the RL decision thread. And now you can see the storage request is represented as an observation vector, which is the state as we have seen it a few slides previously. The state is being fed to an inference network. which will have certain Q values. They're called for what action should be taken. We take the maximum of these values to read out the action that was decided by Cibil. This action will be performed on the HSS, which then, out of which then the reward comes or will be calculated. And then we bundle the action, the state, and the reward together to have something called an experience, which will be stored into what is called the experience buffer, which is inside the DRAM. And so here we can already see the asynchronous execution. Basically, the RL decision thread just stores the experience into the buffer for the RL training thread to asynchronously retrieve, and then how it looks inside of the RL training thread now. It takes a batch of the experience buffer, uses it as a training data set, and then performs gradient descent on the training network in order to do a periodic policy weight update in the end. Yes, and that happens every 1,000 page requests. Now, what we have is that Cibil has a negligible latency overhead compared to the latency of an SSD request, of an SSD I/O request for a very fast SSD. And the memory overhead is also less than 124.4 kilobyte, which is pretty low. So as for the evaluation of Cibil and the key results, now let's first start off with the evaluation methodology. It was evaluated on real systems with various different HSS configurations using the following devices. So first, you had a low-end HDD device, which is rather slow compared to the other devices. But it has a lot of storage. You have a low-end SSD, and then there's the middle-end, a middle-end SSD device, which is used for another configuration, and a high-end Intel Optane, which is very, very performant. And so the CPU being used is just an AMD Ryzen 7. That's pretty standard. So the different configurations there are the cost-oriented, which would be combining high-end and low-end. So that would be the very high-end SSD together with the low-end HDD. And HNL stands for high-end and low-end. Performance-oriented is another configuration, high-end and middle-end, HNM, which has a high-end SSD together with a middle-end SSD. So the first one is trying to have good performance, but you care more about the cost, and the second one is you care more about the performance at a reasonable cost. So 18 different workloads were used from the MSR Cambridge and FileBench suite, which is a storage benchmark. So for state-of-the-art data placement baselines were compared against Cibil. There's CD and HPS, which are heuristic-based, and there is Archivist and RNN-HSS, which are supervised learning models. So also note, none of them have online learning. So the cost-oriented HSS configuration has a, so it consistently outperforms all of the baselines. You can see here again, it's a similar graph as for the, as we have seen before in the x-axis, you see the workloads, the normalized average request latency. And you can see the latency is lower for all of the baselines for Cibil, and Cibil is also pretty close to the Oracle. And for the performance-oriented HSS configuration, you have a 21.6% performance improvement, which comes from Cibil dynamically adapting its data placement policy. And now, this is already a pretty good result, but what you can notice is that Cibil actually underperforms compared to some baselines on two workloads here, so on some workloads. This comes from the fact one has to note that these workloads are very write intensive and have a very random access pattern. And so Cibil had trouble fitting to this access pattern, but nonetheless, Cibil achieves, so nonetheless, there's this 21.6% performance improvement. And also, to go further, Cibil achieves 80% of the performance of an Oracle policy. As we have seen, the Oracle policy is the best possible latency that it could have achieved. So, as for the performance on try HSS, a notable thing about Cibil is if you extend it to more devices, all you need to do is add a new action, and then also in the state add a certain feature, which is the capacity of the new device, remaining capacity that was added. So just minor changes to the Cibil implementation. And Cibil will automatically adapt to this, and it still outperforms rather good the state-of-the-art. So it outperforms the state-of-the-art data placement policy by 48.2%. And so also, as I have just then explained, there's really quite an ease of extensibility when you go from dual hybrid to tree hybrid. So as for Cibil's overhead, we have grazed upon it. It's 124.4 kilobyte of total storage costs. That includes the experience buffer and the inference and training network. So that's a very low overhead. You have 40-bit metadata overhead per page for state features. And you have an inference latency of 10 nanoseconds. You have a training latency of 10 microseconds. And so you can notice, as for the area overhead, it's very small, and for modern systems, rather negligible. There's a small inference overhead. It is by multiple orders of magnitudes lower than the latency of a fast SSD access, and which all satisfies keeping the prediction latency as low as possible. So yes, as for other results that are also interesting, you have a very high throughput of IOPS. So yeah, compared to the other baselines, IOPS is the how do you say, IO requests per second. You have so the performance on unseen workloads also outperforms the baselines. So if you test Cibil on workloads that it has never seen before, compared to testing the other data placement policies on workloads they've never seen, Cibil really manages to adapt its policy and outperforms most of the baselines. And for mixed workloads, so if you mix multiple workloads together and do sort of so let them run almost concurrently, or like bundle them together and make them run randomly, you have equally high performance as if it was just single workloads. So yeah, as for the conclusion, to recap quickly, so we have seen that Cibil is the first reinforcement learning based approach to data placement policies. It provides ease of adaptivity, and so it provides adaptivity, extensibility, and also a big ease of design and implementation. And Cibil, as for the evaluation, it was evaluated on real systems, so you can really see what it would look like in the real world. And it has an improvement of 21.6% compared to state-of-the-art baselines. And it achieves 80% of an Oracle policy that knows all future access patterns and always takes the right decision. So let's move on to the critique and the discussion. Now, I found as for the strength of the paper, it is so a big strength of it is that it's the first paper to use reinforcement learning, a reinforcement learning based approach to data placement policies, which is quite a breakthrough in the field. It is so yeah, I found it very good that the evaluation methodology was on real systems. There are other reinforcement learning papers that don't talk about hybrid storage systems now, but that were being tested on not in the real world, but only through emulations. And here you can really see how reinforcement learning acts for data placement policies in real systems. Cibil is open source, which adds to the ease of implementation, and that's a very good design choice. And the results obviously are pretty convincing. So not only is Cibil a completely new way of approaching data placement policies for hybrid storage systems, but also it outperforms the state-of-the-art data placement policies. And another good thing about Cibil is that its behavior is explainable. So it's not just some machine learning model that's a black box out of the behavior, where from the behavior you just cannot guess what the patterns are, what it's doing, but somehow it still has a good latency. But through experimentation, you can actually recognize patterns and choices of Cibil's data placement policy. So as for the weaknesses, one could talk about the limitations of the RL approach in general. Even though now there is this adaptivity and extensibility, ease to design Cibil itself and to implement it into your operating system, there still remains quite an engineering effort for hyperparameter tuning. You need to do a lot of experimentation to figure out what are the correct hyperparameters. That is, the dimensions of your neural networks, what experience buffer size, etc., etc. And also another limitation is that yes, there is a small memory overhead, but what that could also lead to is that there is less exploitation of data, which comes, for instance, which would come from a too small experience buffer size. Now we have seen for the H&M configuration, for the performance-oriented configuration, there were some workloads in which Cibil underperformed, and that came from the fact that they were so random, because the experience buffer didn't have those patterns, couldn't store all of the patterns of the, or rather, if you look at it in this way, if you have a pattern which is over 2,000 requests, IO requests, but you only have a experience buffer size which can have 1,000 requests, then you cannot figure out this pattern. And so there's always going to be a limitation of the RL approach or of Cibil. And this goes also into hyperparameter tuning. You need to manage to figure out the good experience buffer. As for Cibil and security, as for another weakness, there's Cibil and security, which hasn't been talked about a lot or at all in the paper. It would have been interesting to see what vulnerabilities come with such an approach, but of course, this probably comes from the fact that it needs further research, and it was also a bit out of the scope of the paper. Now, another thing is that the paper could have delved a bit more into why RL works. Now, it shows that, first of all, how it works, and also that it works. It shows this experimentally through comparing it to baselines. But it would have been interesting to see on a more abstract manner why reinforcement learning works and why it mathematically makes sense to use it in for data placement policies. But this also probably needs further research, and yes, it's more of a minor point. Now, I would move on to the discussion if there are any questions, maybe. No questions? Okay, then I will move on to the discussion. Our first discussion point will be about Cibil and security. So I just talked now about it, and I wanted to know from you guys, what do you think would be, if you were trying to sort of break the RL agent or damage its behavior, what would you try to do? So here, what vulnerabilities can you think of that Cibil is affected by? So how would you, as a hacker, attack Cibil? Maybe you have some idea. Yeah.
Yeah. Maybe create some kind of artificial pattern, such that you like disturb the learning process.
Mm-hmm. In order to confuse it, you mean?
Yes,
for instance.
something like that.
Yeah. That's pretty good. Any other? Okay, then I guess, well, your solution was pretty good. So the idea would be you could confuse the RL agent by feeding it bogus workloads and bogus patterns. What you would do, maybe 2 out of 3 workloads are just completely random and make no sense. And that way you could have a performance impact. And since RL is just going to do something completely wrong, you might even do specific patterns which will teach it to only use the slow storage device, in which case you could have an even bigger performance impact, or also reduce lifetime of storage devices if you use only one single device. So there are things in this direction you could do. For the next discussion point, I would like to talk about Cibil and reward. Now, Cibil only uses latency as a metric for reward. I want to know from you, do you think if that's enough? Also, so I will give you a few metrics, and maybe you can tell me if you would use these metrics or if you think it's important for Cibil to optimize for these metrics. First, there would be the hit rate of the fast storage device. And there would be the evictions, the hit rate of the fast storage device. I mean, I think it's self-explanatory. There would be the eviction rate. So how many times are you evicting on average pages from the fast storage device to the slow storage device, and you would give a negative reward for that. There would be energy consumption. You could optimize for that, and quality of service. For instance, for large-scale servers where you have many users that access it, you want to give a minimum possible quality of service and a minimum possible latency, or maximum, let's say. Sorry. So I don't know if anybody wants to join in. Yes, sure.
I think his rate is like already.
There's the microphone.
I think hit rate is already somewhat included in latency. What might be useful is like the worst latency we have in, let's say, 1,000 requests or something like that, to have the single worst performance as a metric as well, to minimize that.
Yes. Okay, that makes sense. Yeah. Anybody else? All right. So yeah. So as for the hit rate, actually in the paper, it was tried. So they have tried to use the hit rate and also the eviction rate with a negative reward, and to add that into the reward of Cibil. And they have found for the hit rate that Cibil will overuse the fast storage device. If you have a high reward for the if you increase the reward for the hit rate of the fast storage device, which would then lead to a lower performance than if you just use the latency. And as for the eviction rate, it's the opposite. It's too scared to evict, to do evictions, which also leads to a lower latency. But your strategy could actually help by not having an increased reward for every single hit rate, if I understood correctly. So yeah.
Yeah, just for it to be more consistent, because that way it might be fine with having a really bad latency in one case for having a better average latency.
Yeah, right. Yeah, I see. So so you mean overusing the fast device storage could have bad latency in some cases, but a better average latency overall, or what? I don't know if I got it. Okay. Well, but either way, this was tried in the paper a bit, and it had unsatisfactory results. Oh yeah, sure. Sorry.
So I have a comment on the first two reward structures that you mentioned. So the challenge there is that, I mean, what Cibil is doing is assigning a reward for every step or for every action. And these two reward structures need to be, let's say, calculated over a period of time.
Yes.
It can't be done for every step.
Yes.
And if you do that, then if you have a deferred reward, then what it also causes is a credit assignment problem, where you can't really credit the agent for a particular action, but it will basically be rewarded for a bunch of actions that it performs. And the agent can also get confused at which action actually improved the performance.
Okay.
So, yeah.
That's right. Also, what I would have chosen from here would be quality of service. I think that could be a good metric to use, because yeah, in large scale servers, you don't really want to compromise on the user experience, and if you just don't have if Cibil now just learns to increase the latency, average latency, and but there are going to be some users who just have a very bad experience, but on average the user experience is good. That's still not what you want to have. And so yes, that would be what I would have chosen. Moving on to the next point. So this is a bit this is about how reinforcement learning is used in other components of a computer architecture. And so they could enter sort of into conflict with each other, especially since if you're using, well, yeah, they could enter into conflict with each other, and they would need to be arbitrated. So I was wondering if you could think of a good strategy to arbitrate different, let's say, conflicting RL agents in the computer architecture. Yeah, that would be basically a question. For instance, a way that so arbitrating, to be a bit more precise, would be, for instance, sometimes you might need to disable an RL agent because it confuses another RL agent. For instance, if the memory would be full, and you would have if the memory is full, often it goes into the storage, and then you could have an RL agent in the memory, which is entering into conflict with Cibil, and if and maybe they could confuse each other, and so you might need to disable, in this case, one or the other, and stuff like that. What could be like a generic strategy to arbitrate this? Any comments, maybe? Should I just give my idea? Or yeah, okay. So this was maybe a bit confusing, but what I would have used is another reinforcement learning agent on top, which can itself learn. So instead of using heuristics or whatever other strategies we have seen, you could use another reinforcement learning agent on top, which just learns, which uses the same strategies in order to learn which agents it should enable or disable, and then you would still have this sort of generality and an ease of implementation. So yeah, that's the idea. And the last point is about the question of whether, so is reward enough? We have seen that Cibil only uses a limited number of state features, and it focuses mainly on reward. So perhaps you might have conjectures on why you think that is, and perhaps do you agree with this approach? Do you think more states should be used, and what do you think about this? Why do you think that mainly reward is being used? And we have seen that for Cibil, for instance, Cibil is much more sensitive to reward, and if you use more states, that has been tried out in the paper, you actually don't get any better performance. So why do you think that is? And do you still think more states need to be used? Yeah. Yes.
Hello. I imagine using more states causes quite of an overhead. So it's probably expensive. And if there's no significant performance gain, why would you add more states?
Yes.
But why there's no performance gain? I don't know, like the reason for that, like maybe these 6 states already cover like the entire space of possibilities.
Yeah. You're right. Yeah, but if you look at other machine learning models, for instance, they would use many more states, and they would still need them. Why do you think for reinforcement learning in particular, in this case, you only need the reward? I don't know if that's if you could think of anything. I wouldn't have thought of it myself.
I don't think so.
I'm sorry. Yeah, basically, perhaps anybody else has a comment. So basically, there's an interesting paper that talks about this, that which is called "Reward is Enough," and it talks about how, in fact, for reinforcement learning, the most important part is the reward, and you really do not need a lot of states in your system, because I mean, this paper is a bit abstract. It also talks about natural intelligence, but basically, if you're in an environment and you want to maximize some sort of reward, you cannot do that without taking into account or without part of this reward maximization being all of the abilities you need to achieve the goal that you want to achieve. And so inside of the reward, you can imagine it like that. You already have many sort of state features that are being that are also an information. So the reward is not only a goal, but also an information for the agent to learn from. So I just thought it was an interesting property of reinforcement learning, how you need much less, in a sense, information, because the information is so telling. So yes, that would be the end of my presentation. I would like to thank my mentors for having helped me through this, and I hope you'll enjoy the next presentation, and thank you for listening. This will be great.
I don't know. I hope.
I mean, too, I don't know.
Thanks.
Giray, maybe I can also introduce Alex now. Do you hear Zoom people?
Yes, we can hear you.
Spectacular.
I actually did not hear Giray.
Anika, can you hear me now?
Yes, very well.
So we are ready. You can introduce.
Okay, sure. So today we'll have a talk about an NDP framework by Alex. Alex is a fifth year bachelor student in computer science. And for now, he's interested in various directions of computer science, including computer architecture. So go ahead, Alex.
Welcome to my presentation about the paper Bisquit, a framework for near data processing of big data workloads. It was presented at the annual International Symposium of Computer Architecture, the 43rd one. So yeah, I will give you a quick overview of what I will be talking about. First, I will give you a short background on NDP, what it is, etc. Then introduce Bisquit. Afterwards, go a little bit into its programming model in more detail. Then provide a more concrete example with the workaround example. Then briefly explain its implementation. Then present selected results and the conducted various tests. And in the end, we will have a short discussion, and I will also talk about strengths and weaknesses, etc. So yeah, but first executive summary. So what's the problem? The problem is basically that prior work mainly focused on proving the concept of NDP or implementing it, but not really on designing a usable framework. There have been some past attempts, but the hardware they use there is either already outdated or...
Excuse me. Sorry, I think it's my mistake. Can I interrupt a little bit? I forgot to share the screen.
Oh, should I start again?
That would be nice, actually.
Okay, yeah, let's start over.
Okay. Sorry for the interruption.
Good practice run.
Okay, you can go ahead.
Yeah.
Wait. Let's get rid of that as well.
I also struggled with sharing my screen.
Okay, go ahead.
So welcome to my presentation about the paper Biscuit framework for near data processing of big data workloads. I will give you a short overview of what I'll be talking about. First, I'll give you some background on near data processing, then introduce Biscuit, its programming model, and give you a short concrete example, word account example, then talk briefly about its implementation. Afterwards, I will present a couple selected results, and in the end, we will have a short discussion, and I will talk about strengths and weaknesses. So what's the problem? The problem is that prior work mainly focused on proving the concept of NDP, near data processing, or implementing it, but not really on designing a framework, a usable framework for it. And if it was done in past attempts, the hardware by now is either outdated or a couple key functionalities like dynamic task loading, etc., are omitted or not implemented. So what's the goal? The goal is basically to design, implement, and also test an NDP framework. And by that, provide basically a blueprint for future attempts or future NDP framework design. So in my opinion, the key ideas that they introduced is using a flow-based programming model and also clearly distinguishing between the computation and coordination model. I will talk later about that. So the results is like the main result, of course, is Biscuit, the framework itself, then the measure performance and the results they on a real system, they get on a real system. And also they ported a database engine, which is probably the most significant application results they provided. So yeah, on the background, I'm sure you're all familiar with it, but NDP stands for near data processing. And well, in traditional processing, we have like our storage where data resides, and we have our processing unit, and we move data from the storage to processing unit, process it, and maybe put it back. So storage is just there to store data. But in a near data processing approach, computation actually also happens either actually inside the storage or really close to it, so that the processing unit can directly fetch intermediate results or final results. And why would you do that? Essentially, moving data from the client to the storage, of the host to storage, it's quite expensive because there's like limited bandwidth, and typically they are relatively far apart, so it's high latency. And that's fine. By applying near data processing, you can use the much higher internal bandwidth of the storage device, for example, SSD in case of Biscuit. And also it allows for more scalability of storage systems in general. And there are also many data-intensive applications that can benefit from near data processing. One example to mention is like a large social network graph. So there's like a lot of pointer chasing, and if you can do that in memory, that's quite beneficial. Also, web page ranking might be an example, or in general, large databases. So Biscuit. Before talking about Biscuit specifically, let's talk about what makes a good framework in general. And the paper provided a couple of key points. One is the ability to run user-written code on a device, which I think it's quite obvious. That's the entire point of the framework. And also provide an abstract and efficient communication between the host application and the storage side tasks. So the tasks that run via near data processing. It's really important such that the user doesn't have to like deal with low-level firmware of the SSD or in communication, which can be quite complex if you're not experienced in that field. Also, there should be efficient resource utilization in runtime. If you don't use your storage side tasks efficiently, I mean, what's the point of NDP? And also, it's important to have an intuitive and high-level programming language or interface such that it's open, or like there's a wide audience that can use the framework, not only people with like deep technical knowledge of computer architecture. And last but not least, what's also very important is safety. You're dealing, like you're processing inside memory, you might overwrite data, you're not allowed to, or delete it or whatever. So you should ensure that that doesn't happen. So why did you choose to design Bisquit? So like already stated in the executive summary, like previous work didn't really focus on designing such a framework. Also, like critical functionalities like dynamic loading and unloading of user tasks were omitted, which made it much more difficult to actually use the framework and develop applications for it with it. Also, what they stated that they want to set a concrete design example for future NDP systems in general. So what is Bisquit? Like in one sentence, a framework that leverages NDP capabilities of storage devices, specifically SSDs. And they made a couple key design choices, which I will like present right now. So they decided to use the flow-based programming model. They implemented dynamic task loading, unloading. They provide high-level language support. In case of Bisquit, it's C++. And also they support thread and multi-core supports such that like the CPU can be used to its most efficiency. So in what kind of storage organizations can Bisquit be applied or used? So what Bisquit basically demands is having a host system with one or multiple SSDs. And they can be organized in various ways. You might have like a directly attached host and SSD, like in your laptop or whatever. You might have multiple SSDs, or you might have a networked system with storage nodes, which again have SSDs. And in principle, in all these organizations, Bisquit can be applied. However, optimizing for all these different kinds of organization is an entirely different problem. So yeah, let's go into the programming model. The fundamental component of the programming model is the SSD-let. SSD-let is a class that describes one unit of computation, essentially. And you can see here an example of the filter class, which is an SSD-let class. Inside the run function, you can define your computation. I mean, you could imagine another class, like a factorial class, where you like compute the factorial of some number, etc. And by having this class, you can then create task instances that perform this defined task. And then another class is application, which basically packages a bunch of SSD-let instances into one. So it's like another layer of abstraction. And the entire thing is flow-based. So the programming model is flow-based. And to make it a little bit more clear, we'll go here through like a short example. So typically, you always start in the host. The host gives the argument or its output, if you will, to the storage side, where the Bisquit runtime resides. And there it then gets, in this specific case, it gets channeled into the first application, application 1, which in this case consists of 2 SSD-let instances. Then inside the application, you get first channel. The first one, some computation is done, then it goes to the second, another computation is done. After that, the output gets channeled into the second application, which in this case only consists of 1 SSD-let. Let's say it could be the filter SSD-let, or we don't know. And after that, it goes back to the host and you have your result. Exactly. So how are these connections built? How do you establish like this task network on the SSD? And to do that, they differentiate between a computation model and a coordination model. In the computation model is realized in the SSD runtime and described by an SSD side module. This module contains various SSD-like classes, like for example, filter class could be part of that. And this module is then loaded onto the SSD. In contrast, the coordination model is realized in the host, like in the and is responsible for creating like the instantiating the SSD-led instances and connecting them the ports, like creating these consumer-producer relationships. And the way it does that is by having a proxy class for every single SSD-led instance on the SSD. So I can then basically say the host can say with its proxy class that the corresponding SSD-led should connect its output to that SSD-led or to that application, etc. Therefore, in a way, the host has full control over the organization of these tasks. So here, how that would look like on hardware, or like representation of it. So what's really important, like this, distinguish the host and the SSD. In the host, you have your like execution environment with main memory, CPUs, etc. Like typical system. And on top of that, you load first of all a library for coordination. It's called libcc in this case, and it provides the functionality that allows the host to coordinate the tasks on the SSD. And then you have the host side program, which defines executing tasks and at the same time coordinates the tasks on the SSD. Then here on the SSD side, you also have an execution environment. It's also CPU, it's a little confusing, but just computational units with computational capabilities. You have DRAM, which is like a slower memory. You have SRAM, which is a little bit faster memory. And of course, it has direct access to the SSD storage channels. And then inside this execution environment, runtime, you have your SSD side module, which contains the different SSD-led classes, and they then can be instantiated to like an SSD-led instance, which then define a running task or like chain of tasks, as you can see here. So let's have a look at a concrete example. I'm sure you're familiar with it. The problem is you have a file with words and you want to count the frequency of each word appearing. So how many times does this word appear? And one solution is to compute in parallel using a map-reduce approach. You have a mapper that tokenizes part of the file into a word frequency 1 pairs, like assigns to every token first a frequency of 1. Then you have a shuffler which orders these tokens. And lastly, you have a reducer which reduces like the same word frequency 1 pairs into a single word frequency pair. And then you have your solution. And here on the image, you can see how this nicely maps to Bisquit. You have your host side program, which then like gives the file as arguments to the different mappers. These mappers are then SSD, like the mappers, shuffler, and reduces SSD-led instances. Then mappers give it to the shuffler and then to the reducer, and you get your result back. So here I will show you how your workflow as a user of this framework would look like. So you first write a host side task, like in C++ in this case, and the SSD side tasks. SSD side tasks are like all the SSD-leds you need. And the host side task is the coordination and maybe additional execution on the host. After it gets compiled down to the host side program, to the SSD side module, the host side program is loaded in the host computer, like the host side, and the SSD side module is loaded into the SSD. And after that, you're basically ready to execute your tasks. Yeah. So regarding implementation, it implements cooperative multithreading. So SSD-leds can execute concurrently, improving performance. I/O ports were implemented using bounded queues. So you can, like the ports that connect SSD-leds and different applications. They implemented dynamic module loading. So out of one SSD-led module class, you can create arbitrarily many, not arbitrarily many, but you can many instances of the SSD-led. And they had to implement dynamic memory allocation. They had to do actually two. They have a system memory allocator that is restricted to Bisquit and for its functionality, and then a user memory allocator which like gives space to the different SSD-led instances, the different tasks running on the SSD. So the results. This is the experimental setup. I think it's not too interesting. You can look at it, but what's important is that they always compare the conventional system, like normal configuration without Biscuit, and then configuration with Biscuit. And as you can see, it was actually done on a real system. Previous work mostly did it like in a simulation. So that's also something they, in a sense, was new. And regarding communication, like one of the fundamental results they provided was communication latency between the different ports. As you can see, everything that goes between host and storage side has much higher latency than the inter-SSD LAT and inter-application port, which like shows you the potential of near data processing. I think it's like, yeah, makes sense. Then for data read latency, you can see that for conventional, it's basically a round trip time from host to SSD back to host. And for Biscuit, it's SSD LAT to SSD storage to SSD LAT. And obviously Biscuit has like a much shorter path. It stays inside the SSD, so it outperforms conventional. Data read bandwidth, in case of conventional system, it's limited by the host interface, which in this case was 3.2 gigabits per second. And Biscuit could outperform this by up to 1 gigabit per second because the internal bandwidth of the SSD is much higher. Or like much by about 1 gigabit. So to the application, they decided to modify Maria database query planner. It ported the database first of all, and they modified the query planner such that certain tasks are offloaded to the SSD. They ran then 22 TPC-H queries, which is a typical benchmark. And they observed that in general, there was a high speed up achieved if there was filtering done with high selectivity. So a lot of filtering, basically. Overall, the execution time improved 3.6 times. So Biscuit performed 3.6 times better than conventional. And also in general, Biscuit had read less pages, like was more efficient with data reads in general. And as you can see on the graph, not every query is present. The reason for that is that not all queries were like suitable for NDP because either they were not data intensive enough or selectivity was too low. So you can see it only performs really well in certain cases, but overall it's an improvement. So we are already at the discussion part. So regarding strengths, I think it's like really strong how they actually like started NDP and finished with like a function implementation of a framework, like designed it, implemented it, tested it on a real system. Also, in my opinion, they highlighted the program model quite well and also made it quite tangible for me with the workaround example. And also, instead of focusing on a single specific workload, they decided to like give a general approach to design, like to give a general framework that might work for various kinds of workloads, which I think can be regarded as a strength. Weaknesses, they mentioned safety like as a key feature of a framework, but they didn't really discuss it. It was maybe like 2 sentences. So they could have maybe elaborated a little bit more on that. So how safety can be ensured and what it really means for it to be safe, the framework. Also, the implementation section, at least for me, it felt quite cramped. It didn't get in the same attention as the programming model, for example. Maybe it's also the point, but I think, yeah, is one small weakness. So I think that said, it's your turn. We are already at the discussion part. So let me ask you my first question, which is, how do you think does NDP or Biscuit specifically affect the traditional role of CPU and storage devices? Do you have an opinion on that? Okay, that's fine. So for me, Biscuit essentially turns the SSD into a CPU with low computation power but high internal data bandwidth. So with such a usable framework, I can imagine like the border between computation unit and storage unit becomes even blurrier, and like they might get closer together. And also an interesting question to ask is how to coordinate different computation devices in a system. For example, how can coherency be maintained? For example, cache coherence or like channel coherency of memory. And if you're interested in that, you can have a look at the paper Conda, which suggests an approach to coherency for near data accelerators. Near data accelerators are like maybe the picture helps. Like accelerators located at DRAM, which basically perform computation, and Conda provides a way to ensure coherence. And one might also ask, how could you maybe extend this to SSDs in case of Biscuit? Next question. Does increasing capacity of main memory mitigate the impact of Biscuit? Yes or no, maybe. So imagine with like infinitely large main memory, is there a need for like having near data processing inside the SSD? Yeah.
No? Oh yeah.
Yes.
Okay. Yeah. Okay. I suppose you would still need near data processing because of the issue you talked about with limited bandwidth and the latency of actually accessing the memory. Also, if you increase the capacity of main memory, maybe you decrease the latency of accesses or something. So it would still be good to have near data processing. I don't know if that makes sense.
Yeah. I mean, imagine you could load everything to main memory, like it would be much faster than having it on SSD on a hard drive. But what about data that's not really used that much, like or like maybe only used once? It's really inefficient to like load a bunch of stuff into main memory to then just use it once and then you don't use it anymore, because in that case the performance is actually bound by the IO latency. So it still makes sense to offload like such tasks to the storage, like with near data processing, even if you have like arbitrarily large main memory, like or high-speed memory available. Does that make sense? Does
Yeah, totally.
Yeah. So do you think could Biscuit influence design of storage devices, and if yes, how? I'm not good at this. So I think potentially, like you might even see storage devices that have increased computational capabilities, because one shortcoming they mentioned in the paper is that the SSD like had quite low computational power, which makes sense as a storage device. And also one might consider that in the future one could co-design the storage device and the programming model, because they at some stage they really struggled, for example, with memory allocation, etc., because like it's not, SSD is not designed for that specifically. So yeah. So last question, I think. Yeah, last question. What applications could benefit most from Biscuit?
I suppose machine learning, especially, no?
Yeah. That's a good one. Machine, like
also all graph processing you mentioned before.
Yes, exactly. Graph processing. Yeah, there are probably countless, like any data intensive application. One specific example, genome analysis. I think I also had a lecture on this. We have like match sequences of genes. If you're interested, you can look at GenStore, which is a system that uses in-storage filters. Another one could be, like you said, machine learning, deep neural networks. The models might not fit in high-speed memory or like main memory. And then things like OptimStore could come to use, which computes model optimization actually in storage, which optimizes performance. And yeah, queries with high selectivity filtering was the example with the Maria database, traversal of large networks, graphs, social graphs, and maybe also in distributed computing, like with like a lot of separated storage nodes, etc. So such that you can reduce data transfer. So I should have
I think that can you go to the previous slide also?
Oh.
Yeah, I think that one of the other aspects that we could emphasize is the features that the applications need to have such that they could benefit from processing near storage. So I think that in this slide, you're providing some application examples, but also some application features in general. I mean, one layer above beyond these examples is also interesting to discuss. So I think that one of the key points we could mention is that applications that touch or access large amounts of data with low data reuse are also in general can be good candidates for processing and storage, but that again always comes at the trade-offs that because you usually have more limited compute resources inside the storage system and also different restrictions on how efficient access patterns work. So in the end, that problem would be translated into, okay, whether we want to tune our storage systems, as you also mentioned in your slides, such that they can enable stronger storage processing systems. But also another point is to design hardware and software together such that with minimum cost, we can adapt the applications for executing inside storage systems. So I think that both of these directions are in general important in this domain. So I wanted to briefly mention that before you summarize the talk.
It's a great point. Thank you. So I should have asked previously, but are there any questions? Feel free to ask. I can also go back to the slides if you have like forgot something. If not, I'm finished.
Okay, thank you. Mohammed, do we have any announcements or something?
So thanks everyone for attending. Please don't forget to attend to the quizzes. And also we have forums to add feedback to the presenter, not only presenters during today's sessions. Please also add your feedback for the previous presenters. Thank you.
Thank you.